Last week, you did a lab where you attempted to verify the law of conservation momentum in one dimension. Today, we're going to try to verify the law of conservation momentum in two dimensions. In other words, you're going to have a collision where two objects, two spherical objects, or two soft balls are going to collide with each other, bounce off of each other, and you're going to analyze the x component and the y component and try to see if both the x component and the y component are conserved. Exactly what I've told you over the last couple of weeks is the case. Okay, we'll see over the next few days as we complete this lab write-up if it is the case. So here's how it's going to work. You're going to have two objects. Okay, some of you are going to have two big yellow round spherical balls like this. Some of you are going to have smaller ones. Doesn't really matter what you have, but you want to have two that are roughly the same. If they're not exactly the same mass, that's fine. I'm perfectly fine with that. In fact, it's a little bit better if they're not exactly the same. But what you don't want to have is a heavy one like this and a light one like this. Okay? Two that are more or less the same, at least the same order of magnitude. And you're going to take those objects and you're going to collide them in a two-dimensional collision. You're going to measure the mass of both of those objects, object 1 and object 2, keep them straight, know which one throughout the entire experiment is number 1 and which one is number 2. You may even want to put a piece of masking tape on it and label it object 1, object 2, so that you don't get them mixed up, because they are going to look a lot alike. Set them up something like this, and then send them by hand towards each other like this. Now, they don't have to be at exactly 90 degrees. You're going to have a really tough time doing this by hand, trying to make it exactly a T-bone or a 90-degree collision. If you luck out and it works out to be exact, then that's great. It saves you a tiny bit of work. If you don't luck out, not a big deal. Okay, the analysis still isn't all that crazy hard. They're going to collide. They're going to bounce apart from each other because there's no sticky tack on them this time. And then they're going to head off in whatever direction. You need to, after you've measured the mass, you need to analyze the before and after motion of both of these objects. Now, how are you going to do that? You can't use the motion sensors that you used for your activity last week. The reason is because that can't possibly deal with two dimensions. It can only deal with one dimension. So we have to have another way. Everybody's got a phone nowadays. So what you're going to do is, within your group of 4, video this. Now, when you're videoing this, be careful. You want to video it from as close to directly above as you can. If you're videoing it from the side, you're going to get what we call parallax error. It's kind of like you sitting in the passenger seat looking at the speedometer of your car. It doesn't read the exact correct number, right? Because you're measuring it from an angle. You don't want to do that with your video camera here. You want to measure it from as close as possible to directly above. Now, it may be impossible to be directly above. Okay, there's a source of error, right? But as close as possible to directly above. Now, you also have to remember that it has to be steady. Your phone has to be steady as you're measuring this or as you're recording this. You don't want to have it bouncing all over the place. So basically what I'm saying, don't hold it by hand directly above. You're better off putting it off the edge of your desk and bracing it with your hand on the edge of the desk, even if it's not directly above, than you are by trying to hold it by hand directly above. We had a couple groups in the last class do it from the bridge in the atrium. Okay, that was great because it gave them a big field of view. The camera was far away from the experiment. Really, really big field of view. Lots of data that they could collect. Okay, and they could be directly above the experiment. It worked out fantastic. Make sense? Now, I mean, it's pretty much, you guys know how to use your phones. You guys know how to collect video on the phones. There's only one other real thing that I got to point out here with the actual collection of data. You need to put somewhere in this field of view a meter stick. You're going to use some software to analyze this video, and you have to tell the software what a meter is. Okay, the software doesn't know what a certain unit of measurement is unless you tell it. So you're going to put a meter stick anywhere in here. By the way, I would suggest you not put the meter stick right here, because when they collide, they're going to hit the meter stick, right? Don't put it there. I said put it anywhere, not anywhere. Don't put it there. Put it over here somewhere. Okay, put the meter stick over here somewhere where the objects aren't going to collide. Maybe even, probably even better, put the meter stick up here, okay, where you know for sure the objects aren't going to collide with the meter stick. We want as close to an isolated system as possible, right? Friction comes into play, all kinds of things come into play. The meter stick could be a pretty huge factor if they hit the meter stick right away after the collision. Make sense? All right. Once you've performed this experiment, once you've defined a meter and you've actually collided these two objects, by the way, remember, you want to have your hand in the video for as small of time as possible. You want to have data both before and after where your hand or no other factors are coming into play. Okay, so make sure that you're not colliding them and your hand still on the objects just before the collision. Make sure you've got time with no hands on the ball before the collision takes place, right? Once you've got that data, you're going to use a software program, not on the Chromebooks up here, but on some laptops that we have up here called Tracker. Now, if you've brought your own laptop, I'll give you a little jump drive with the Tracker software on there that you can run it on there, okay, whether it's a PC or a Mac. You're going to email the video to yourself, or you're going to upload it to your Google Drive, or you're going to get it to your computer somehow. Okay, I don't really care how you do it. Probably email is the best way to do it. But however, you're going to get it to your computer, and then you're going to save it to your desktop or somewhere else, some other folder that you can find it. Yeah, I don't really care where you put it. Save it somewhere where you can find it. Desktop might be the best place. Then you're going to open the file by clicking on this open button right here. Once you've opened the video, it should look something like this. Okay, you see a video in the frame in the frame there now. Now, in that frame, you should see probably two objects. But if you don't see two objects, it just means that maybe one of the objects was out of the frame, the video frame, before the video was started. Okay, as long as it appears at some point in the frame, that's okay. It's not the end of the world if you see it there right away. Also see the meter stick that I've got there? So object 1, object 2, and we get the meter stick right there. The first thing that you want to do in here, and again, this is addressed in the handout that I gave you, okay, but I just want you to understand this so that you can follow the steps in the handout when you actually get this. First thing you want to do is click on the axis button up here. What that does is defines a frame of reference for this. Okay, when we measure velocity or we measure position, we have to have a frame of reference. We have to tell it where to measure from. Now, in the end, your frame of reference could be the moon, for all I care. It doesn't really matter where your frame of reference is defined, as long as it stays the same throughout the entire experiment. So you can see in this one that I've got a frame of reference that I've moved to the bottom left-hand corner of my video. It doesn't matter if you put it in the bottom left-hand corner or top right or middle. It doesn't matter, as long as it stays the same throughout the entire experiment. Once you've got that frame of reference defined, then what you have to do is define what your meter is. So essentially, you're going to define what we call a calibration stick. You're going to click on the Tracks button on the toolbar up at the top here. Then you're going to click on New right there. And then you're going to click on Calibration Tools right there. And then Calibration Stick right there. Then you're going to adjust that calibration stick right here to line up with your meter stick. Now, if your entire meter stick is in your video, then you might as well just define 100 centimeters as the entire length of the meter stick. But if you're like me and only part of your meter stick is in the video, that's okay. Just define, as I have here, 30 centimeters on 30 centimeters of the meter stick. It doesn't really matter as long as it's a correct measurement of your meter stick. So now we're actually ready to collect data. We've got our frame of reference defined. We've got our meter, or in this case, 30 centimeters defined. We're ready to collect some data. So how do we do that? Now we have to define our two masses, our two objects. So you're going to click on Create. Again, you've got these instructions in front of you as well. You're going to click on Create Point Mass. Then you're going to do that for the other object. So basically, you want to create two point masses. Point mass A, point mass B. And then you're going to click on one of the masses, probably mass A, whichever one you define as your first object, mass 1, mass A, whatever you're calling it. Click on that object right up here. Once you've done that, you're going to hold the Shift key along with clicking your mouse at every point along that ball's movement. So if this is object A, you're going to put your mouse right here. You're going to hold the Shift bar and click your mouse. That's going to define the first position of object A. It will automatically fast forward the frame to the next frame where you'll click Shift, click. Next frame, Shift, click. Next frame, Shift, click. Go all the way through before and after the collision for object A. Then, down here, scroll to wherever you need to scroll to do the same thing with object B. Make sense? What you don't want to do is start analyzing right here because my hand is still touching it right there, right? So before you start analyzing it, scroll forward a little bit until my hand has left contact with the ball so that we have as close as possible to an isolated system. Once you've done that, you should see a bunch of data appearing in the bottom right-hand corner. That's the data that you're going to copy and paste into a Google Sheet, plot some graphs, and do your thing. So how do you do that? Click on one of these numbers, doesn't matter which one. Control A, which selects all the data. Control C, which copies it. Go into Google Sheets from Google Classroom, create a sheet in Google Classroom, go into that spreadsheet, Control V will paste it. Then you want to do the same thing by clicking on Mass B. Control A, Control C to copy, Control V in Google Sheets to paste. Then you might see a graph that looks like, once you plot these graphs, you might see one that looks like this. Well, this would be initial velocity. This would be final. Separate them into initial and final velocity like you did in your last activity. Maybe you see it like this. What does that mean? Well, you get negative velocities. How can we have negative velocities? Well, it depends on how you define your frame of reference. It doesn't matter. It doesn't make any difference. If it's negative, though, just make sure you put a negative value in for it. Okay? Separate them. If you get some data before that kind of looks like this, delete that, right? We want this and we want this ultimately plotted as two separate graphs so we can get initial velocity and final velocity. All right, good news. Couple pieces of good news. In this experiment, you only have to do data, analysis, conclusion, sources of error, 4 things. More good news. In this activity, I've already got a template for the write-up copied for you in your Google Classroom. So when you go into Google Classroom, click on the assignment, the document that you hand in is already there. And it's going to look exactly like this. You will fill in the blanks. Now, there's quite a few blanks to fill in. The first thing you got to fill in is 8 graphs, right? 8 graphs. Initial x velocity, object 1. Initial y velocity, object 1. Initial x velocity, object 2. Initial y velocity, object 2. Final, and so on and so on and so on. 8 different graphs. Put them in order of this. These are your 8 graphs. Put them in that order, please. Makes it easier for you to mark it. Once you have the values of those velocities from the slope of your graphs, plug them in here. Just type them in right there. And then go to your analysis. Your analysis consists of 6 calculations. Initial x momentum, pi, x component, m1 v1i plus m2 v2i. Remember, x's, only the x's. Final momentum for the x's. And then your percent difference calculation, which you've done before, is actual minus theoretical over theoretical times 100. Now, which is the actual, which is the theoretical? You tell me. What's the actual value here, initial or final? What's the theoretical value? Good. So your theoretical value would be pi. your actual value would be PF. That make sense? You actually should end up with your theoretical value, which is your initial momentum. You're going to repeat that for the y component analysis that we see right there. So we get x component, we got y component. And then finally, for your conclusion, was momentum conserved in the x component? Yes or no? Was momentum conserved in the y component? Yes or no? How do you know? Sources of error? There's a few sources of error that you can find here, some pretty important sources of error. We'll see what you can do with them, okay? Give me 2 or 3 good ones. Okay?